Welcome to Theory of Computation. This is lecture number 37. Today we will continue our discussion on space complexity. In the last lecture, we introduced space-bounded Turing machines. We defined what it means for a Turing machine to take space S of n, and then we looked at some simple Turing machines and we analyzed how much space do they require in order to do their calculations or computations. After that, we actually devised two space-efficient algorithms, and they were for very familiar problems. The first problem was satisfiability. As you know, satisfiability is NP-complete. However, we observe that satisfiability can be solved in linear space since we can reuse space over and over again. And the algorithm or the Turing machine that requires linear space and solves satisfiability is extremely simple. It is the most trivial algorithm that you can think of. The algorithm is simply go through all possible assignments and see if one of them is satisfying. And this requires linear space because we can reuse the space over and over again in order and check if a given assignment satisfies our formula, our Boolean formula or not. So what we realized is that linear space seems to be extremely powerful. We can even solve NP-complete problems in linear space. So it is not true, it's not obvious that if we can solve a problem in less space, that means we can quickly solve it. The reason is because space can be reused over and over again, whereas time doesn't seem to have that property. The second thing we did was we looked at the emptiness problem for non-deterministic finite automata. And then we devised a non-deterministic linear space algorithm for it. Let's revise what we did and see what does it tell us. Here we look at a non-deterministic linear space machine. We start with the language, which is the emptiness language for non-deterministic finite automata. And this language consists of all descriptions of NFA such that the language of these NFAs is empty. So this language consists of description of all NFAs which do not accept anything. What we devised a non-deterministic linear space algorithm that decides the complement of this language. So the complement of this language will consist of description of all NFAs which accept some string. Well, the first idea was for this Turing machine to guess that string which will be accepted. Using simple facts from automata theory, we were able to show that there must be a string of length at most 2 to the q, which will be accepted by such a NFA which accepts something. The second thing was we used the idea of not actually writing down that whole string, but guessing it symbol by symbol while performing our simulation on the NFA. And this led to a linear space algorithm that decides the complement of this language. Let's see what was the theorem that we proved. We showed that the complement of the emptiness problem for NFA is in non-deterministic space N, or it is in non-deterministic linear space. Now, it is very interesting to note that this problem, the emptiness problem for NFA, is neither known to be in NP nor is it known to be in co-NP. So non-deterministic linear space may actually contain problems which are neither in NP nor in co-NP, and this is such a candidate problem. So non-deterministic linear space actually may be an extremely large class of problems, and it may contain some problems which require a lot of time to solve. However, they can, and a lot of non-deterministic time to solve. However, they can be solved in non-deterministic linear space. Once again, this emphasizes the fact that space and time are two different measures. They may not have too much to do with each other. Now what we want to do is we want to study extremely important problem in space complexity called the reachability problem. This problem is very central to space complexity, and you would see this problem will pop up over again when we start looking at log space and non-deterministic log space. In some sense, you can say this is the quintessential problem in space complexity. Let's have a look at it. Let us say we are given a directed graph G with vertices V and edges E. And let's say that a vertex T is reachable from S if there is a path from S to T. How can we solve the reachability problem? So, what you're given is a graph, a large graph with vertices in it, and it's a directed graph, and two special vertices. One is called the S stands for source, and T stands for the terminal vertex. And all you want to know is if there is a path in this graph from the source vertex S to the terminal vertex T. And the question that we want to investigate now is, how do we solve this problem, and how do we solve this problem in a space efficient way? So let us formally define this language R. R here stands for reachability, which is going to be the set of all encodings of G, ST, where G is a graph and S is a vertex in G which is reachable from T. So what you're given is a graph G and two vertices, and the question that is asked is it possible for me to start from the vertex S, use the edges of this graph, and eventually reach the vertex T? That's the computational question. The question is, given a graph and two vertices S and T, decide if there is a path from S to T. You have already studied this kind of problem, this particular problem, in your algorithms course, and you must have studied several algorithms for this problem. Let's see how will we solve this problem. You learn actually two algorithms to solve this problem. One of them is called depth first search, and the other one is called breadth first search. The rough outline of this algorithm is the following. So I'm giving you a rough outline of an algorithm which, by filling in details or making changes to it, you can either get depth first search or breadth first search. Let's look at how these algorithms work. Well, the algorithm first marks S, the start vertex. And now we repeat n-1 times the following thing. If we find an edge from a marked vertex to an unmarked vertex, so suppose A is a marked vertex and there's an edge going from A to a vertex B and B is not marked, then we mark B. We repeat this loop n-1 times, and at the end of this loop, if T gets marked, we accept, we know that there's a path from S to T, otherwise we reject. So this is an algorithm. What it does is it simply starts with S and says, okay, S is reachable from S, and then it marks S. And then in the next step, it tries to reach another vertex from already vertices that are known to be reachable from S. If it finds one, it marks that. And it continues like this. And at the end of the algorithm, if T ever gets marked, then T is reachable from S, otherwise it is not. You study this algorithm in detail. You study various implementations of it. One of them is called depth first search, the other is called breadth first search. Both of these algorithms, you know, require linear time when implemented on a computer, and they're extremely efficient. Usually the emphasis when you study these algorithms is on analyzing the time complexity of these algorithms. DFS and BFS are efficient implementation and elegant implementation of this underlying algorithm that I've told you. And they also have other desirable properties, which we will not go into, which you study in your algorithms course. But they are just simply efficient implementations of this idea. However, now we want to view these algorithms from the point of view of space complexity. So rather than what you do in your algorithms course and analyze DFS and BFS from time complexity point of we want to say how much space do these algorithms take. The point to notice is that both these algorithms require us to mark vertices which are initially all unmarked. Therefore, we need to have at least one bit for each vertex, and we set it when we mark that particular vertex. Thus, the whole algorithm would take linear space. Suppose that the graph has n vertices. We need at least n bits, which will keep track of which vertex is marked and which vertex is not marked. Initially, we'll set all these n bits to say 0, indicating that all the vertices are unmarked. Then we'll go and mark S and set that bit to 1 and continue the algorithm. And in the end, we'd look at the bit that corresponds to the vertex T, and see if that is set, and if that happens, we accept, otherwise we reject. But the point is that at least n bits are needed in implementing these algorithms. Therefore, these are linear space algorithms. The interesting question now is, can reachability be solved in sublinear space? In fact, as we will see later, reachability is one of the most important problems in complexity, especially space complexity. What we are now going to do is look at an ingenious space-efficient algorithm for reachability. So what I will describe to you now is a space-efficient algorithm for solving this reachability problem. And once we study this algorithm, we'll see how these ideas have very direct applications in the space complexity. Let us say we have a graph G with vertex set V and edge set E, and it's a graph on n vertices, and we are given two vertices A and B. We say that B is reachable from A via a path of length K if there exists vertices V0, V1 all the way up to Vk, where V0 is A, Vk is B, such that each Vi and Vi plus 1 form an edge in the graph. So what we say is that you have a vertex A here and you have another vertex B here. Now, if there is a path of length K from A to B, then we say B is reachable from A via a path of length K. This is a very simple definition from graph theory. We'll be needing it in our subsequent discussion. Now, let us begin with the following very simple facts. The first fact is that if B is reachable from A via a path of length K greater than 2, then there is a vertex C such that the first thing that holds is that C is reachable from A via a path of length K over 2. And the second thing that holds is B is reachable from C via a path of length K over 2. How will you prove a fact like this? Well, suppose if I tell you that there is a vertex A and there is a vertex B, and I can go from A to B by taking at most K steps. What you have to show me is that you can go to a vertex C from A in at most K over 2 steps, and then from C to B in at most K over 2 steps. Well, the candidate vertex C is staring us in the face. It's the middle vertex on this path, because then the distance from A to C is going to be less than or equal to K over 2, and the distance from B to C to B is going to be less than K over 2. So this is a very simple graph theoretic fact to verify. Let's look at the second fact. If B is reachable from A, then it is reachable from A via a path of length at most n, where n is the number of vertices in the graph. And this is also a very simple fact. It says that suppose in a graph, if you're given two vertices, then you can go from A to B by taking some number of hops, then you don't need to take more than n hops. And the proof of this is, suppose you can go from A to B via a path, and this is not a simple path, then this path must have a loop. Or if this path has length more than n, then one of the vertex must repeat. Now you can cut off this loop, and that still makes a path which leads you from A to B. Thus, if you're given a non-simple path from A to B of length more than n, then you can convert it, shortcut it to obtain a path which has length at most n from A to B. So these are two very, very simple graph theoretic facts, and we will use these two facts to come up with our algorithm. It's actually very surprising how these two simple facts will be used ingeniously to come up with this space-efficient algorithm. Let's notice two other tiny facts. One is that B is reachable from A via path of length 0 if and only if B is equal to A. Well, that is just a consequence of the definition of being reachable from A to B via a path of length 0. In this case, the path k is equal to 0, so V0 has to be equal to A, and it also has to be equal to B. Therefore, A has to be equal to B. Let's look at the second tiny fact. If B is reachable from A via a path of length 1, if and only if A comma B is an edge in the graph. Once again, this is also a simple consequence of the definition of being able to be reachable from A via a path of length 1. That means you have to have a direct edge from going from A to B. Now what we will do is we will write a function which we call reach A comma B comma K. So this function will have three parameters, two vertices and a number. So A will be a vertex in the graph, B will be a vertex in the graph, and K will be a number. This function will return true if B is reachable from A via a path of length at most K. So this function is going to do more than just solve reachability for us. If you give it two vertices, you are also allowed to specify the length. So you can give it a vertex A and B, and say for example you give it k equals 30. Then if from A you can reach B in at most 30 steps, this function will return true. Otherwise it will return false. So k is an extra added parameter. It is controlling the length of the path that you're looking for. So if k is equal to 0, then this problem is extremely easy to solve. All we have to do is check if A is equal to B and return true, otherwise return false. And this would return the correct answer, and that's given to us by the tiny fact. Similarly, if k is equal to 1, then we either check that A has to be equal to B or A comma B has to be edge in the graph, and we return true, otherwise we return false. So in these two cases, these are the terminating cases for this recursive function. Otherwise, we call this function recursively. So if these two cases don't happen, then k must be greater than or equal to 2. Now what we do is we loop through all the vertices in the graph. So C goes through all the vertices in the graph, and we check to see recursively if we can reach from A to C in at most k over 2 steps, and we can reach from C to B in at most k over 2 steps. If both these conditions are met, then we know that we can reach from A to B in at most k steps, and therefore we return true. However, if we cannot find any such vertex, then there is no way to go from A to B in less than or equal to k over 2 steps, and therefore we return false. So the correctness of this program or this function is obvious from the facts that we have already stated. The boundary cases or the terminating cases are correct, and if we assume that this function works, then by induction it works because we had the fact 1 to help us say that if we can reach from A to B in k over 2 steps, then there is a C such that we can go from A to C in k over 2 steps and from C to B in k over 2 steps, and therefore this function gives the correct answer. And so this function does solve the problem that we're talking about. Now the question is, how much time does it take and how much space does it take? Well, remember, we're not interested in time complexity now. We're only interested in space complexity. For those of you who are very interested in time complexity and are intrigued by this question, I would ask you to go and try to analyze how much time does this function take. But for you, I will just analyze how much space does this function take? And we'd see that this is an extremely space-efficient algorithm. We can solve the reachability problem now by simply calling reach s, t, n. But the question is, how much space will that take? This is a recursive program, and we need to analyze the space requirement of this recursive program. And as you know, and you have analyzed recursive programs in your data structures course, in your algorithms course, that recursive programs put things on the stack. And if you look at the space requirements of this program, you realize that there are hardly any local variables. So the local requirements of this program are virtually nothing. It's only what is kept on the stack that adds up to the space used by this program. So let's do that analysis. There are 3 parameters that are passed and 1 local variable. C is the local variable. These have to be put on the stack. So how much space do these variables take? Let's look at how much space these variables take. Well, we have 2 names of vertices and 1 number. That's what we need to store on the stack. If the vertex set of the graph is given the numbers 1 up to n, then each vertex can be stored in log to the base 2 of n bits. So to store each vertex, all you will have to do is store its name, which you can store in log n bits. And so storing the name of a vertex requires log n bits. Similarly, the parameter k is a number between 1 and n. That's because we initially call this function with k equals n, and then subsequently k is decremented, so it can never go above n. So the number k also requires us only log n bits and can be stored in log n bits. So we have 3 parameters, each one requiring about log n bits. So the total things that are being put on the stack each time are a required space order log n. This each call will require us to store order log n space on the stack. So the space requirements of this function are order log n times the depth of the recursion. So the question is, how deep does this recursion go? What is the depth of this recursion? Let's think about it. Well, we start with the parameter k equals n. And let's concentrate on this parameter, because once this parameter reaches either 0 or 1, the recursion terminates and we do not call this function recursively anymore. So we start with k equals n. At the next step, k is halved. In both the calls, k is halved. So whatever is being put on the stack, then in the next call, k is halved. So we go from n to n over 2, and then it's halved again, n over 4, and then it's halved again, n over 8, and then it's halved again, n over 16, and so on and so forth. So the question is, how many possible times can we halve n before we reach either a 0 or a 1? Well, you guessed it right. If you're going to take n and start halving it, before you reach 1, you would have at most halved it log of n time. Therefore, the depth of the recursion is only log of n. Since we start with n and recursively, each recursive call reduces it by a half. Hence, the total space requirement of this program are order log squared of n. So what we have done is analyze this program, and we've proved the following theorem. Reachability is in space log squared n. And this is a deterministic algorithm. So what we have shown is that the problem of reachability can be solved in order log squared n space. Now, this is sublinear amount of space. This is, log squared of n grows much slower than n. So this function requires sublinear and extremely tiny amount of space in order to solve this reachability problem. Now let us prove a very simple relationship between time and space complexity. So we have been studying space complexity. Before that, we studied time complexity. Now what I want to do is relate the two and ask if there is any obvious or non-obvious relationship between time and space complexity. Let us say M is a deterministic Turing machine that uses space Sn. So I have a Turing machine which uses space Sn. The question is, can we give an upper bound on the time taken by this Turing machine M? So I have a Turing machine M, and S of n is the amount of space used by this Turing machine. The question is, can I give any intelligence, can I give any upper bound on how much time will this Turing machine take? Well, in order to answer this question, let us count how many configurations of M are possible on an input of length n. So we go back to our model and we look at that model, and you give this machine an input of size n. Now when this machine computes, it can go through various configurations. Of course, some of the configurations may occur in the computation, some of them may not occur. The first thing we want to do is we want to come up with how many possible configurations are there. Once we know that, we'll be able to say something meaningful about how much time does this machine take. Note that we can specify any configuration of this Turing machine by writing down its tape contents, and the only thing that we need to write down is the tape contents of its work tape. Furthermore, there are only Sn cells that are going to be used. Therefore, all the tape contents can be written down in a string of length Sn. The other thing that we need to do to specify a configuration is we will have to specify the position of the two heads. The first head can occupy at most n possible positions, since it is allowed to only scan the input, and the second head can occupy any position on the work tape, and there are S of n positions that it can occupy. Thus, I can give the whole configuration by giving 2 positions of the tape head and all the tape contents of the work tape. Now, how many possible configurations would there be? N for the choices for the first head, S of n choices for the position of the second head, and B to the Sn possible strings of length Sn which can be on the work tape. Thus, there are n times Sn times B to the Sn possible configurations. Here, B is the number of symbols in the work alphabet of this Turing machine. So, what we have is now an upper bound on the total number of configurations that this machine can conceivably have. Next, what we can do is we can prove the following theorem. And this theorem says that if M runs in space Sn, then there are at most 2 to the order Sn distinct configurations of M on X. Well, for this we have already counted the number of distinct possible configurations of M on X, and they can be at most n times Sn times B to the Sn, and the only thing we note is that this quantity is 2 to the order S of n. Next, we can prove this theorem which says that if M accepts an input in space Sn, then it accepts it in time 2 to the order S of n. Well, why is this the case? Well, suppose a Turing machine accepts an input in space Sn, then I claim that it cannot repeat any configuration. Well, since it's a deterministic Turing machine, if it repeats any configuration, then it is in an endless loop, because it's going to keep on repeating itself. Therefore, each configuration at every time step must be different from all previous configurations, and since these are the total number of configurations, therefore the machine must halt in this much time. And this gives us a simple upper bound on the number of steps taken by a Turing machine that is space bounded. And if you think about it, this theorem is true for both deterministic and non-deterministic Turing machine. If there is a non-deterministic Turing machine that accepts input in space S of n, then it accepts its input in non-deterministic time 2 to the order S of n. So, what we realize is that there is an exponential relationship between time and space, but we can only make a one-sided space statement. Suppose somebody tells you that their Turing machine takes space S of n. You can immediately say that the machine does not take time more than 2 to the order of S of n. But you cannot be sure that it does take much less time than that. But you can be sure that it does not take more than 2 to the order S of n steps or 2 to the order S of n time. That's an upper bound on the time that you can give with a guarantee. Now, let us define the analogs of P and NP from a space complexity point of view. Remember the classes P and NP, which we studied in time complexity. Remember how important they were. Remember that we said that P is the set of all problems that we consider that we can solve in practical time. In these are problems that we consider tractable from a time point of view. These are problems that require only polynomial time. And NP was its non-deterministic analog. And NP actually turned out to be extremely important complexity class because it led us to the theory of NP completeness, which allowed us to identify many hard problems, many difficult problems, many interesting problems, and it led us to one of the most beautiful questions in complexity theory called P versus NP. So it's only natural that we try to play the same game with space complexity. We define the class P space and NP space. So let us define P space to be the set of all problems that we can solve in polynomial space using deterministic Turing machines, and NP space to be the set of all problems that we can solve in non-deterministic polynomial space. So roughly what we're saying is P space is the set of all problems for which we can solve in practical amount of space. Here we're not saying anything about time. We're just saying that we only need practical amount of space to solve these problems. Similarly, NP space is the non-deterministic analog of P space. These are problems that we can solve in non-deterministic polynomial space. The analog of the P versus NP question for space computation is, of course, very natural. It is the question, is it true that P space equals to NP space? Well, remember that for time complexity, we ask the question if P is equal to NP. And we realize that this is one of the most difficult questions in computer science, one of the most important celebrated questions in computer science. It has $1 million prize on it, and for a very good reason it has that prize. I think the prize is very little. Similarly, we can ask the analog of this question in space complexity. Unfortunately, there is no prize on this problem. The reason is because this problem has already been solved, and this problem was solved by Savage, who proved that P space is equal to NP space. We will prove this theorem. In fact, we will prove a more general theorem. As a consequence, we will get this theorem which says that P space is equal to NP space. Roughly, let's see what this theorem is saying. Well, remember, for some good reason, we said polynomial time was practical. Now what we're saying is polynomial space is practical amount of space that we are willing to give in order to solve a problem. And what this theorem is saying is that polynomial space, if you're going to view space complexity from polynomial space point of view, then non-determinism and determinism look exactly the same. They don't differ. That doesn't mean that non-deterministic space and deterministic space are always coinciding. We'll see a question where we suspect they may coincide or may not coincide, where we will actually have a beautiful unsolved problem. However, this is saying if you're looking at things from a polynomial point of view, then non-deterministic space and deterministic space are exactly the same complexity classes. You don't need to distinguish between them. They're equal. Well, in order to prove this theorem, we'll prove a much more general theorem. Let's look at that theorem, which we will call Savage's theorem. This theorem says that suppose f of n is a function which is greater than n, then non-deterministic space f of n is contained in deterministic space f squared of n. So, what does this theorem say? This theorem says that you can get rid of non-determinism at a quadratic blow-up in space. So if you're willing to accept a quadratic blow-up in the space requirements, then non-determinism can be gotten rid of. You can take any Turing machine that takes space f of n and convert that Turing machine. Savage will give you a recipe for converting this Turing machine into a deterministic one, and the deterministic Turing machine will only use quadratic the amount of space that the non-deterministic Turing machine was using. Of course, once we have this theorem, as a consequence of this theorem, we obtain that P space is equal to NP space. The reason is this: if you have a non-deterministic Turing machine that runs in polynomial time, then it runs in time, let's say, n to the k. Using Savage's theorem, you can convert that non-deterministic Turing machine into equivalent deterministic Turing machine with only a quadratic blow-up. But square of a polynomial is a polynomial, and therefore the new Turing machine will also require polynomial time. So Savage's theorem is extremely important, and the ideas used in it are extremely beautiful. Now what we want to show in order to show this theorem is that if L is a language that is accepted by a non-deterministic Turing machine in space order f of n, then it can be accepted by a deterministic Turing machine that uses space order f squared of n. The main idea is the one that we used for solving reachability. In fact, the main idea is reachability. Indeed, what we can do is we can view this question as a very special reachability question. Let's look at the details. Let n be a non-deterministic Turing machine that accepts a language L in space f of n. We will build a deterministic Turing machine M that accepts L in space f squared of n. This deterministic Turing machine M will simply check if an accepting configuration of n is reachable from the starting configuration. And this word, reachable, gives away the whole clue. All what we are going to do is we are going to design this new deterministic machine M, which will try to solve the following reachability problem. Starting from the initial configuration of the non-deterministic Turing machine, can we reach a accepting configuration of the non-deterministic Turing machine? Let's think about this for a moment and see what we are actually embarking on. Imagine the non-deterministic Turing machine and imagine all its configurations strewn around you. And what you do is you go and pick the initial configuration of this Turing machine on an input X. Well, now what you do is all the configurations that are strewn around you, if a particular configuration yields another configuration in one step, then you put an arrow in from that configuration to this new configuration. Well, this way you will get one huge, gigantic graph. And the only thing that you want to know is whether in this graph, is from the initial configuration, is it possible for you to reach an accepting configuration? If you can do that, then the non-deterministic Turing machine accepts that input. And if no accepting configuration is reachable from this configuration in this gigantic graph, then the non-deterministic Turing machine does not accept this input. And so what you're trying to do is trying to solve a reachability problem in an implicit graph, and this implicit graph is gigantic. So all you have to do is use the same procedure, the space efficient procedure, reach A, B, K that we came up with before, and see if you can replace each step in there, because in that problem we assumed that the graph was given to us explicitly. Now somehow the graph will be given to us implicitly by describing the Turing machine n to us and the input x to us. And this can be done, and then we can analyze how much space does that take. Let's go ahead and do that. Let us define a problem called yieldability. Suppose we are given two configurations C1 and C2 of a non-deterministic Turing machine n and a number t. The question is the following: can C1 yield C2 in t steps, in at most t steps? So now yieldability is a problem in which you're given three things: configuration 1, configuration 2, and a number t. And you have to answer the question if you can go from the configuration C1 to C2 in at most t steps of this non-deterministic Turing machine. The non-deterministic Turing machine is also given to you. We furthermore assume that we are also told that this Turing machine will only use space f of n. So we are also given a guarantee that this non-deterministic Turing machine will only use f of n to go from configuration C1 to C2. All we have to do is we have to tell whether the Turing machine can do this in at most t steps or not. This looks extremely familiar to the reachability question. Well, now let's consider the following algorithm which will solve this problem for us. We call this function can yield C1 C2 t. So this function also takes two parameters. Now if t is equal to 1, then what we do is we check if C1 is equal to C2. If C1 is equal to C2, then you can go from C1 to C2 in 0 steps. Otherwise, we check the rules of the Turing machine n and see if it is possible to go from C1 to C2 via the rules of n. And this can be done by observing the Turing machine and seeing if there is a transition which takes us from the configuration C1 to C2. So this is the base case, and this can be easily done. Now for the next case. Now suppose if t is greater than or equal to 2, then what we do is we take every configuration C prime of length at most f of n, and we check if we can yield from C1 C prime in less than or equal to t over 2 steps, and if we can yield from C prime to C2 in less than or equal to t over 2 steps. If we can, then we return true. But if this fails for all possible configurations C prime, then we return false. So the fact that this function k yields returns the correct thing is once again obvious. If you can go from a configuration C1 to C2 in t steps, then there must be an intermediate configuration that you go to in t over 2 steps, and then from that go to C2 in t over 2 steps. Thus, the correctness of this can yields function is absolutely obvious. What we need to do is analyze how much space does this take. Once again, this is a recursive program, so we have to see how much space does it require. And what it does is it stores things on the stack. And the analysis is going to be exactly like the reachability question. How much space does each configuration require if we want to store it? Well, remember, we said that each configuration is of length at most f of n. So each configuration takes at most order f of n space to store. Furthermore, if we call can yield C1, C2, t, then the depth of the recursion would be log to the base 2 of t. Well, this is the same argument that we repeated for reach a, b, k. Over there, k was being halved at each recursive call. Here, t is being halved at each recursive call. So before t reaches 1, they can be at most log to the base 2 of t steps, and therefore the depth of the recursion is going to be log of t at most. Now, given a tm m and input x, let us consider the following deterministic Turing machine. This Turing machine takes as input x, it computes f of n. Now it lets C0 to be the initial configuration of m on x. Then for all accepting configuration C sub f of length at most f of n, it checks if we can yield from C0, C sub f in 2 to the order f of n steps. If that is the case, it accepts, otherwise it rejects. What we claim is that this algorithm is going to accept exactly the same language as the one that is accepted by the non-deterministic Turing machine. Why is that the case? Well, we already argued that if a Turing machine runs in space Fn, then it must accept its input in time 2 to the order f of n steps. Therefore, we are checking it for enough time. And then we use the can yield procedure and we try all possible final configuration. Therefore, this would be a correct algorithm which would accept exactly the same strings that are accepted by the non-deterministic Turing machine n. The question is, how much space does this take? It is clear that if m accepts x in space f of n, then the above algorithm will also accept x. On the other hand, if m does not accept x in space f of n, then the above algorithm will reject. The space requirement of the above algorithm are f of n times the depth of the recursion, which is log of 2 to the order f of n, which turns out to be conveniently order f of n times f of n, which is order f squared of n. So we have come up with deterministic Turing machine that simulates this non-deterministic Turing machine and requires time f squared of n. This completes the proof of our theorem, and this also completes the proof of Savage's theorem, which says that p space equals to np space, or another way to remember this theorem is that one can get rid of non-determinism at the cost of quadratic blow-up in space. Well, however, there is a slight technicality that is left and that I want to address in the last few minutes of this lecture. If you see the algorithm, we've said that we'll compute f of n. However, we may not know how to compute f of n. F of n is, of course, it may be an extremely difficult function to compute because it may not be a simple function. It is the number of cells required by this Turing machine, and we may not know it. So how do we compute f of n? Well, there are two ways to circumvent this difficulty. One is we can say that we are talking about functions which can be computed in space f of n, and therefore this is not a problem, and we can add that assumption in our theorem. Another way to get rid of this difficulty is somehow try to guess f of n. What would be the value of f of n? We may not be able to guess f of n, but given an input x, we can easily find out what is the largest amount of space that would be ever used. What is the amount of space that will be ever used on this particular input? And this can be done as follows. We can start with the value f equals n and start increment this value till we find the length of the largest configuration that we can get to from the initial configuration. We can use this value of f now to see if m reaches an accepting configuration of length f. Now, if we look at this theorem, we've put aside this minor technicality that we will discuss in the next lecture in detail. I'll show you how this is done, how we can get rid of this assumption. Nevertheless, if we put this technicality aside, we realize that we have proved that if we have a non-deterministic Turing machine that runs in space f of n, then we can come up with a deterministic Turing machine that runs in space order f squared of n. The above theorem, of course, shows that n space n to the k is contained in d space n to the 2k, and therefore P space is equal to N space. So today what we have done is, in just one lecture, we've been able to solve the P versus NP analog, the space analog of that question, and what we've been able to show is that P space is equal to N space. In the next lecture, we'll continue our discussion on space complexity, the exciting things to come. I'll see you next time. Thank you and goodbye.